When we assign a value to a variable, LWPython creates or updates an entry in the variables map. For example, when LWPython executes the following statement, Python creates the entry z5 in the variables map. However, when we assign a list to a variable, the list is not directly added to the variables map. Instead, LWPython stores the list in another place called the object store and stores the index or the location of the list in the variables map. The object store is an LW stack that contains Python objects. Objects include collections such as lists and dictionaries, as well as class instances. We will study dictionaries and classes later. The object store is initially empty. When a list is assigned to a variable, LWPython first pushes the list to the object store. For example, when LWPython executes the statement x equals list 517.321, Python pushes the list 517.321 to the object store. Thus, the object store becomes the following stack. Next, LWPython creates an entry in the variables map. As usual, the entry key is the target x. The entry value is the index of the list in the object store, which is 0. But when LWPython sees an entry x0, it assumes that x contains value 0 rather than location 0 in the object store. To avoid confusion, LWPython instead creates a Python reference as follows. Now, suppose that we want to retrieve the element at index 2 as follows. LWPython will first retrieve the value at key x in the variables map. The entry value is Python reference 0. Since the reference is 0, Python retrieves the element at index 0 of the object store, which is the list 517.321. Now that LWPython has the list, it can retrieve the element at index 2, which is 3. Why does LWPython store lists in the object store instead of the variables map? Let's begin this discussion with a simple example. Consider this program. In line 1, Python evaluates the expression 5, then stores it in x. In line 2, Python evaluates the expression x, then stores the result 5 in y. At this point, the variables map contains two entries, x5 and y5. Finally, in line 3, Python stores 8 in x. At the end of the program, the variables map is x8 and y5. Now let's compare this with a slightly different program. In line 1, Python evaluates the list 1, 2, 3, then stores the result in x. Let's try storing this list directly in the variables map as we did with integers. Then after line 1 is executed, the variables map contains one entry with key x and the value list 1, 2, 3. In line 2, Python evaluates the expression x, then stores the result in y. After line 2 is executed, the variables map contains two entries with keys x and y and the value list 1, 2, 3. Finally, in line 3, Python assigns 9 to x2. Then x becomes the list 1, 2, 9. And what is y? Python didn't touch y, so y is still the list 1, 2, 3. Thus, x2 is 3, while y2 is 9. Now we know that Python actually behaves quite differently. For instance, Python stores lists in the object store rather than the variables map. But you may not have known that when Python assigns 9 to x2, y2 also becomes 9. Wait, we never asked Python to change y. What happened? The idea is that when we assigned x to y in line 2, x and y became the same variable. Thus, any changes in x are also reflected in y. This explanation makes sense, but it is inconsistent with Python's behavior in the first example. Although we also assigned x to y in the first example, assigning 8 to x did not affect y. Curiously, Python uses a different rule when x is an integer. Instead of pointing both x and y to the same container, Python copies x's container into a new container. Since x and y use separate containers, changes in x do not affect y. So why are lists and integers treated so differently? For some clues, let's carefully walk through the second example. The object store and the variables map are both initially empty. After LWPython executes x equals list123, the object store contains one element, which is the list123, and the variables map contains one entry, which is x and Python reference 0. The object store contains the actual list, and the variables map just contains a reference to that list. After LWPython executes y equals x, the object store still contains one element, and the variables map contains a new entry with y and Python reference 0. As before, LWPython evaluates the expression, which is x, then assigns the value to the target, which is y. X is Python reference 0, so Python assigns Python reference 0 to y. Thus, both x and y point to the element at index 0 of the object store. Finally, after LWPython assigns 9 to x2, the element in the object store changed to the list 129. X and y still point to the same object, so y2 is also 9. Notice that LWPython did not make a copy of the list 123. This is potentially a big advantage because copying list elements can take a long time and occupy a lot of space. The benefit is not obvious when the list is small, but software engineers regularly encounter collections that contain thousands or even millions of elements. And just so we're clear, we can still copy a list if we want to. For example, we can write a loop that copies the list elements one by one. One downside of this model is that programmers need to mentally keep track of variables that point to the same object. If we're not careful, we may unintentionally change variable values. For example, if we forget that x and y point to the same element in the object store, we may think that a statement like x2 equals 9 only affects variable x, when it also affects y. This can lead to unexpected program behavior. Here's a fun idea. What if we stored variable names instead of references in the variables map? For example, what if the variables map contained the following entries: y with a list 123 and z with y? In this model, variables themselves are references. LWPython probably could accommodate this model, but the expression evaluation process would become more complex. For example, suppose that we ask Python to evaluate y. Python would look up the variables map as usual, but Python first needs to check the type of the entry value before pushing anything to the value stack. If y is a single value, then Python would push the entry value as usual. But if y is a list, then Python would push y to the value stack. In contrast, storing references in the variables map allows Python to evaluate references in the same way as other types of variables. As an added bonus, the object store model is much closer to Python's actual behavior than the variable as reference model. Try some list operations on the simulator, paying close attention to the variables map and the object store.